Welcome to Sleepless Astronomer, where we explore the wonders of space and the universe. If you're enjoying these cosmic journeys, please like this video and subscribe to the channel. We post new videos every single day, so you can tune in whenever you want to learn about the cosmos. And we'd love to hear from you in the comments. Let us know where in the world you're watching from. We always enjoy connecting with fellow space enthusiasts around the globe. Now let's begin tonight's journey through the universe. How extraterrestrial plants could photosynthesize. Photosynthesis, the process by which plants, algae, and certain bacteria capture light energy and convert it into chemical energy, powers most of Earth's ecosystems. Green plants absorb sunlight, split water molecules, combine carbon dioxide from the air with hydrogen from the water, and produce sugars while releasing oxygen as a byproduct. This process transformed Earth's atmosphere from oxygen-poor to oxygen-rich over billions of years, enabling the evolution of complex animal life. Photosynthesis seems so central to life that we naturally wonder whether alien plants on distant worlds would photosynthesize in similar ways. The answer is nuanced. While capturing energy from starlight would likely be advantageous for life on any illuminated world, the specific chemistry and mechanisms of alien photosynthesis would differ dramatically depending on the star's properties, atmospheric composition, available pigments, and evolutionary history of each world. On Earth, photosynthesis centers on chlorophyll, a complex molecule containing magnesium at its center, surrounded by a ring structure that absorbs light strongly in the red and blue portions of the spectrum while reflecting green light, which is why plants appear green. Chlorophyll's absorption spectrum is not random but reflects the properties of sunlight. Our Sun is a yellow dwarf star with a surface temperature around 6,000 degrees Celsius, emitting light most strongly in the visible portion of the spectrum that our eyes evolved to see, with peak emission in the green-yellow range. Plants evolved pigments that absorb the abundant wavelengths while reflecting the less useful portions. But most stars in the galaxy are red dwarfs, cooler, smaller stars with surface temperatures around 3,000 degrees that emit most of their light in the red and infrared portions of the spectrum. A planet orbiting in the habitable zone of a red dwarf would receive much less visible light and far more infrared radiation than Earth receives from our Sun. Photosynthetic organisms on such a world would need to adapt to this shifted spectrum, likely evolving pigments that absorb infrared light rather than visible light. Capturing infrared photons presents challenges because each infrared photon carries less energy than a visible light photon. On Earth, chlorophyll uses two photons, absorbed at different stages of photosynthesis, to extract enough energy to split water molecules, which requires significant energy input. With lower energy infrared photons, alien photosynthesis might need to capture 3 or even 4 photons per reaction to gather sufficient energy, making the process less efficient. However, red dwarf stars are extremely common and extremely long-lived, shining for trillions of years compared to the Sun's 10 billion year lifespan. So even if photosynthesis is less efficient under red dwarf light, organisms would have enormous amounts of time to evolve and adapt. The pigments that absorb infrared light would likely appear black or very dark to human eyes because they would absorb nearly all visible light in addition to infrared. A forest on a red dwarf planet might be covered in black vegetation, maximizing absorption of every available photon from the dim red star. This is the opposite of Earth's green plants, which reject green light as insufficiently useful. On a planet where photons are precious, wasting any light would be disadvantageous, so evolution would favor organisms that capture everything. Conversely, planets orbiting hot, bright blue or white stars would receive intense ultraviolet radiation, along with visible and infrared light. Ultraviolet photons carry high energy, potentially too much energy, as UV light damages DNA and proteins. Photosynthetic organisms on such worlds might evolve pigments that specifically avoid ultraviolet absorption, reflecting or dissipating UV light while capturing only visible wavelengths. Or they might evolve protective mechanisms, UV-absorbing compounds in outer cell layers, extremely efficient DNA repair systems, or pigments that can safely handle high-energy photons by converting excess energy into heat or fluorescence. The colour of alien plants would thus depend on their star's spectrum. Under orange K-type stars, plants might be red or orange, reflecting the most common light while absorbing other wavelengths. Under blue stars, plants might be yellow or orange. The specific colours would depend not just on what light is available, but also on what pigments evolution happens to discover and what combination of wavelengths provides optimal energy capture. Multiple pigments working together might be advantageous. On Earth, plants contain several pigments beyond chlorophyll, carotenoids, that absorb blue and green light, appearing yellow, orange, or red, and other accessory pigments that expand the range of useful wavelengths. These accessory pigments capture light that chlorophyll misses and transfer the energy to chlorophyll for use in photosynthesis. Alien plants might evolve even more diverse pigment systems, with perhaps 5 or 10 different pigments, each specialized for different wavelength ranges, collectively capturing a broader spectrum than Earth's photosynthetic organisms manage. The electron transport chains that actually convert light energy into chemical energy might use different chemistry than Earth's photosynthesis. On Earth, photosynthesis splits water molecules to extract electrons, releasing oxygen gas as waste. But water splitting is energetically demanding. It requires significant light energy input. An alien photosynthesis might use different electron donors that are easier to oxidize than water. Hydrogen sulfide, for instance, is easier to split than water and was likely used by early photosynthetic bacteria on Earth before oxygen-producing photosynthesis evolved. A planet with abundant hydrogen sulfide might develop photosynthetic life that remains at this stage indefinitely, producing elemental sulfur rather than oxygen as waste. Ion compounds, organic molecules, or even molecular hydrogen could serve as electron donors in alternative photosynthetic pathways. Each would produce different waste products. Ion photosynthesis might precipitate iron oxides. Organic-based photosynthesis might produce various carbon compounds, and hydrogen-based photosynthesis might produce protons that combine with other elements. None of these would generate an oxygen-rich atmosphere, demonstrating that photosynthesis doesn't necessarily equal oxygen production. The carbon source might also vary. Earth plants use carbon dioxide from the atmosphere as their carbon source, but CO2 concentrations vary dramatically across different worlds. Venus has a thick CO2 atmosphere, but is far too hot for life as we know it. Mars has thin atmosphere that's mostly CO2, but overall, CO2 availability is low due to the low pressure. A planet with very low atmospheric CO2 might require photosynthetic organisms that can concentrate and capture CO2 extremely efficiently, perhaps with specialized structures or enzymes far more effective than Earth's plants possess. Alternatively, alien photosynthesis might use carbon sources other than CO2. Carbon monoxide, methane, or even dissolved bicarbonate in water could provide carbon for building organic molecules. Each source would require different enzymatic machinery and would produce different end products. Methane-based photosynthesis might produce more complex hydrocarbons, essentially reversing the process that creates methane on Earth. ICO-based photosynthesis might build organic molecules through different chemical pathways than CO2-based photosynthesis uses. The physical structure of alien photosynthetic organisms might differ radically from Earth's plants. Trees evolved on land where structural support is needed to compete for sunlight, growing tall to shade competitors. But on a planet with perpetual dense cloud cover, blocking direct sunlight and providing only diffuse illumination, there would be no advantage to height. All locations would receive similar light levels. Plants might remain low-growing, perhaps forming dense mats rather than tall structures. On a planet with a very thin atmosphere, providing minimal structural support, perhaps Mars if it ever hosts photosynthetic life, organisms might need to be extremely sturdy and low profile to withstand wind without atmospheric cushioning. Or on a high-gravity world, the structural challenges of growing tall might be prohibitive, keeping photosynthetic organisms close to the ground in spreading horizontal forms rather than vertical trees. Aquatic photosynthesis might dominate on ocean worlds. Earth's oceans contain vast amounts of photosynthetic organisms, phytoplankton, algae, and photosynthetic bacteria, that drift or swim in the water column, capturing sunlight in the upper illuminated layers. On a world covered entirely by ocean, with no dry land, all photosynthesis would necessarily be aquatic. These organisms might evolve greater efficiency at capturing dim light filtered through water, or might develop gas-filled structures to regulate their depth, staying in the optimal light zone. Deep-sea photosynthesis might even be possible using not sunlight, but the faint light produced by hydrothermal vents or bioluminescence. On Earth, some photosynthetic bacteria near deep-sea vents use the faint thermal radiation from the hot vent fluids. This produces very little energy, but it demonstrates that photosynthesis isn't absolutely dependent on sunlight. An alien world with extensive hydrothermal activity might develop photosynthetic life that uses volcanic light, living in eternal darkness sustained by geothermal rather than solar energy. Bioluminescence-powered photosynthesis could create bizarre ecological cycles where organisms generate light through chemical reactions, other organisms use that light for photosynthesis, and the products of photosynthesis support the light-generating organisms. This would be less efficient than using a star's light directly. But on a rogue planet drifting through interstellar space with no star, such a system might be the only way photosynthesis could exist at all. The efficiency of photosynthesis varies greatly on Earth, with most plants converting only 1 to 2% of incoming light energy into chemical energy stored in sugars. This low efficiency reflects various constraints and trade-offs in the photosynthetic machinery. Alien photosynthesis might achieve higher efficiency through different molecular mechanisms, different pigment arrangements, or different metabolic pathways. Alternatively, on worlds where light is extremely dim, even 1 or 2% efficiency might be insufficient, driving evolution toward photosynthetic systems that capture and convert light more effectively, perhaps achieving 5 or 10% efficiency through molecular innovations not present on Earth. Timescales of photosynthesis might differ on other worlds. Earth's photosynthesis operates on timescales of milliseconds to seconds for individual reactions, constrained by the speed of enzyme reactions at Earth's temperatures. On a very cold world, reaction rates would be much slower. Photosynthesis might take minutes or hours for reactions that complete in seconds on Earth. This would mean slower growth rates and organisms that live life in slow motion from our perspective. On a hot world, reactions might proceed faster, allowing rapid photosynthesis and potentially faster growth, though this would also require dealing with the instability of biological molecules at high temperatures. The evolution of photosynthesis on Earth took hundreds of millions of years, with simpler forms appearing first and the complex, oxygen-producing photosynthesis we see in plants evolving later. On alien worlds, the evolutionary trajectory might differ. Perhaps photosynthesis evolves quickly, becoming established within the first billion years of life's appearance. Or perhaps it never evolves at all, with life remaining dependent on chemical energy from geological processes rather than light energy. Photosynthesis, while extremely useful, is not inevitable. It requires specific evolutionary innovations, including light-sensitive pigments, electron transport machinery, and carbon-fixing enzymes. A planet might have abundant life that never discovers photosynthesis, remaining microbial and chemosynthetic indefinitely. The seasonal variations on alien worlds would influence photosynthetic strategies. A planet with extreme axial tilt might experience dramatic seasonal variations in light availability, requiring photosynthetic organisms to either hibernate during dark seasons, store energy during bright seasons, or maintain alternative metabolic modes that don't require light. A tidally locked planet with one side permanently facing its star would have a permanent light side and permanent dark side, with photosynthesis possible only on the lit hemisphere or in the twilight zone between light and dark. The atmospheric chemistry would affect what wavelengths reach the surface. Earth's ozone layer absorbs harmful ultraviolet light, preventing it from reaching the surface. A planet without an ozone layer would expose surface organisms to intense UV, requiring either UV protective mechanisms or restriction of photosynthetic life to water, which naturally blocks UV. A planet with a different atmospheric composition, perhaps with sulfur compounds, nitrogen oxides, or exotic hazes, would filter light differently, creating different wavelengths available at the surface, and thus different optimal pigments for photosynthesis. How extraterrestrial plants could photosynthesize encompasses a vast range of possibilities shaped by stellar spectra, atmospheric filtering, available chemistry, and evolutionary contingency. From black plants absorbing every photon under dim red suns to colourful organisms reflecting abundant high-energy light under bright blue stars. From water-splitting oxygen producers to hydrogen sulfide users releasing sulfur. From rapid tropical growth to slow cold world metabolism, alien photosynthesis would adapt to each world's unique conditions while performing the same basic function, capturing light energy and converting it into chemical energy that powers ecosystems, potentially creating oxygen-rich atmospheres, modifying planetary chemistry in detectable ways, and revealing through their presence that life has discovered on distant worlds what it discovered on Earth. That starlight, properly harnessed through molecular machinery, shaped by billions of years of evolution, can power the chemical reactions that sustain living things, turning distant stars into energy sources for biology across the galaxy. How evolution would work on other worlds. Evolution is not a theory specific to Earth. It is a fundamental principle that must operate wherever life exists, as inevitable as gravity or thermodynamics. The basic mechanism is elegantly simple. Organisms that are better suited to their environment tend to survive and reproduce more successfully than those less well suited, passing their advantageous traits to offspring. Over countless generations, this process of natural selection shapes organisms to fit their environments with remarkable precision. Charles Darwin recognized this principle in the 19th century by studying finches on the Galapagos Islands and countless other organisms, but the principle extends far beyond Earth. On any world where life emerges, evolution would be the engine driving biological diversity and adaptation, though the specific outcomes would be shaped by each world's unique conditions. The fundamental requirements for evolution are remarkably minimal. Life must be able to reproduce, creating offspring. There must be variation among individuals. No two organisms are exactly alike. Some of this variation must be heritable, passed from parents to offspring, and there must be differential survival and reproduction. Some variants survive and reproduce more successfully than others. These conditions create evolution automatically, inevitably, as surely as releasing a ball on a slope causes it to roll downhill. Any replicating system with heritable variation and selection will evolve, whether it's based on DNA, some other information storage molecule, or even non-biological replicating systems. On Earth, DNA serves as the information storage medium for nearly all life. The DNA molecule consists of two strands wrapped around each other in a double helix, with each strand composed of a sugar phosphate backbone and a sequence of 4 bases: adenine, thymine, guanine, and cytosine. The sequence of these bases encodes genetic information, and this information is copied when cells divide, passed to offspring when organisms reproduce. Mutations, random changes in the DNA sequence caused by copying errors, radiation, chemical damage, or other factors, create the variation upon which natural selection acts. But DNA is not the only possible genetic molecule. Scientists have created synthetic alternatives called XNAs, xenonucleic acids, that can store information and be copied, yet use different sugars or even different backbone structures than natural DNA and RNA. These artificial genetic molecules demonstrate that information storage and heredity don't require DNA specifically. An alien organism might use a completely different molecule to store genetic information, perhaps based on different chemistry more suited to its world's conditions. A very cold world might favour genetic molecules that are stable and flexible at low temperatures. A very hot world might favour molecules that resist heat degradation. The specific molecule doesn't matter. What matters is that it can store information, be copied with reasonable but imperfect fidelity, and allow variation to arise. The timescales of evolution would differ dramatically on different worlds. On Earth, bacterial generations might span minutes to hours, allowing rapid evolution. The bacteria that cause diseases evolve antibiotic resistance within years or decades, as antibiotics create selection pressure, favouring resistant strains. In contrast, large organisms with long generation times evolve more slowly. Elephants with generation times of decades evolve far more slowly than bacteria. On an alien world where organisms have extremely long lifespans, perhaps living for thousands of years, evolution would proceed at a glacial pace from a human perspective, with significant changes taking millions or billions of years. Conversely, on a world where organisms reproduce very rapidly, evolution might proceed at dizzying speeds. If alien microorganisms reproduced every few minutes, like some Earth bacteria, they could evolve through thousands of generations while we watched. Such organisms might adapt to new conditions, almost in real time, developing resistance to threats or exploiting new resources faster than slower evolving species could respond. The environment determines what traits are advantageous. On Earth, giraffes evolved long necks because reaching high branches provided access to food that shorter animals couldn't exploit. Cheetahs evolved extreme speed to catch fast prey. Cacti evolved to store water and reduce surface area in desert environments. Each adaptation reflects the specific challenges and opportunities of the organism's environment. On alien worlds, different environments would favour different adaptations. On a high-gravity planet, evolution would favour short, stocky body plans with strong skeletons and powerful muscles to support body weight against stronger gravitational pull. Tall, slender organisms would be at a disadvantage because the structural demands of supporting height would be too great. Flying organisms might be rare or absent because overcoming gravity to achieve flight would require enormous energy expenditure. Over millions of generations, organisms would become increasingly adapted to moving efficiently under high gravity, perhaps developing 4 legs or even 6 or 8 for stability, with low centres of gravity and massive muscular systems. On a low-gravity world, the opposite pressures would apply. Organisms could afford to be tall and slender because less structural support is needed. Flight might be easy, favouring the evolution of wings and aerial lifestyles. Animals might leap enormous distances because the energy required to overcome gravity would be minimal. Over time, organisms might evolve increasingly delicate structures, abandoning the heavy skeletons and dense muscles necessary on higher gravity worlds in favor of lighter, more energy-efficient body plans. Atmospheric composition would profoundly influence evolution. On Earth, the transition from an oxygen-poor to an oxygen-rich atmosphere about 2.5 billion years ago, the Great Oxidation Event, was catastrophic for organisms adapted to the old atmosphere. Oxygen was toxic to them, and they retreated to oxygen-free refuges or went extinct. But for organisms that could tolerate or use oxygen, this chemical change created opportunities. Oxygen metabolism releases far more energy than anaerobic metabolism, enabling the evolution of larger, more active, more complex organisms. The size of organisms on Earth is ultimately limited by how efficiently they can deliver oxygen to their cells. On a world that never develops an oxygen-rich atmosphere, organisms might remain permanently small and metabolically limited. Without the high energy yield of oxygen metabolism, active lifestyles like those of birds, mammals, or even fish might be impossible. Life might consist entirely of small, slowly moving organisms eking out existence on the limited energy available from anaerobic metabolism. Or evolution might discover entirely different high-energy metabolic pathways based on different oxidizing agents, perhaps sulfur compounds, chlorine, or substances we haven't considered. The availability of water determines many evolutionary paths. On Earth, life originated in water, and even terrestrial organisms remain fundamentally aquatic. Our cells are filled with water, and we constantly need to replenish water lost to evaporation and excretion. On a water-rich world with extensive oceans, evolution might produce countless aquatic species, but might never develop terrestrial life if there's no advantage to leaving water. On a dry world with limited water, evolution would favor organisms that conserve water ruthlessly, perhaps evolving impermeable skins, efficient kidneys, metabolic water production, or even the ability to extract water from food or from humidity and air. Predation creates powerful selection pressures that drive evolutionary arms races. Prey evolve defenses, armor, toxins, speed, camouflage, while predators evolve counter-adaptations to overcome those defenses. Stronger jaws, detoxification mechanisms, greater speed, better sensory systems. This coevolution produces increasingly sophisticated organisms on both sides. On Earth, the evolution of predators coincides with the evolution of many complex features: eyes to detect prey, brains to process sensory information and coordinate hunting strategies, complex behaviors for stalking and capturing prey. On alien worlds, predation would likely emerge wherever life becomes sufficiently complex, driving similar evolutionary arms races, but the specific adaptations would reflect the alien environment. On a world with dense fog or darkness, evolution might favor chemical or acoustic sensing over vision. On a world with three-dimensional environments, like open water or thick forests, predators might evolve better spatial perception and three-dimensional maneuverability. On a world where prey can burrow or fly, predators would evolve means to follow them into those refuges. Sexual selection, where organisms choose mates based on specific traits, creates another evolutionary force. On Earth, peacocks evolved elaborate tails, not because those tails help survival, but because peahens prefer males with impressive tails. This sexual selection can drive the evolution of traits that actually reduce survival, but increase reproductive success. On alien worlds, whatever traits the choosing sex prefers would be amplified through generations, potentially creating wildly extravagant features that serve no purpose beyond attracting mates. Convergent evolution, where unrelated organisms independently evolve similar solutions to similar problems, demonstrates that certain designs work well for certain challenges. Eyes evolved independently many times on Earth because detecting light provides such valuable information that natural selection repeatedly favored organisms with improved light-sensing abilities. Wings evolved independently in insects, birds, bats, and pterosaurs because flight provides such significant advantages that multiple lineages evolved aerial capabilities. On alien worlds, convergent evolution would operate similarly. Any organism that needs to move quickly through water would likely evolve a streamlined body shape because physics dictates that this shape minimizes drag. Any organism that needs to see would likely evolve some structure that focuses light onto photosensitive cells, though the specific implementation might differ. Any organism that needs to manipulate objects would likely evolve some form of grasping appendages. The specific details would vary. Alien hands might have 3 fingers or 7, might be at the end of tentacles or rigid arms, might use suction or hooks instead of friction, but the basic function of grasping would emerge wherever it provides advantage. However, historical contingency, the accidents of evolutionary history, also plays a crucial role. Vertebrates on Earth have 4 limbs because that's what the early fish that first crawled onto land happened to have. There's nothing inevitable about the number 4. If a 6-limbed fish had been the first successful land colonizer, terrestrial vertebrates might all have 6 limbs today. On alien worlds, similar historical accidents would lock in features that become constraints on all future evolution. An early successful body plan might dominate an entire planet's evolutionary tree, with all descendants constrained by that ancestral architecture. Mass extinctions reset evolutionary trajectories. On Earth, the asteroid impact 66 million years ago that killed the non-avian dinosaurs allowed mammals, previously small nocturnal creatures, to diversify into the enormous variety we see today. Without that extinction, mammals might have remained small and marginal while dinosaurs continued dominating. On alien worlds, whatever catastrophes occur, asteroid impacts, volcanic eruptions, climate changes, nearby supernova, would similarly reset evolution, wiping out dominant groups and allowing previously marginal organisms to radiate into newly available ecological roles. The speed of environmental change influences evolutionary dynamics. Rapidly changing environments favour organisms with short generation times and high mutation rates that can adapt quickly. Stable environments favour organisms optimised for efficiency in unchanging conditions. An alien world with a highly variable climate, perhaps due to an eccentric orbit or an unstable star, would see evolution favouring adaptable generalists. A world with stable conditions for billions of years might produce highly specialised organisms, exquisitely adapted to narrow niches, but unable to cope with change. Intelligence itself is an evolutionary adaptation that emerged on Earth because it provided survival and reproductive advantages. Brains require enormous energy. Human brains consume about 20% of our total energy, despite being only 2% of body mass. This high cost means intelligence only evolves when its benefits outweigh its costs. On Earth, intelligence apparently provided sufficient advantage through tool use, social cooperation, and problem solving to justify the expense. On alien worlds, whether intelligence evolves depends on whether similar advantages exist. Some environments might favour intelligence more strongly than Earth did. A highly variable environment where adaptability is crucial might select strongly for intelligence and behavioural flexibility. A world where organisms compete primarily through social manipulation rather than physical prowess might favour intelligence. Conversely, some worlds might never produce intelligence because simpler solutions always work well enough. If food is always abundant and predators are absent, the energy costs of maintaining a large brain might never be justified. How evolution would work on other worlds follows the same fundamental principles that operate on Earth: variation, heredity, and selection, but expresses those principles through the unique circumstances of each world. A high-gravity planet would sculpt short, powerful organisms. A dark world might favour chemical sensing over vision. A frigid world might produce organisms with anti-freeze biochemistry and slow metabolisms. Each world would develop its own evolutionary history, branching from simple origins into complexity through billions of years of selection, extinction, radiation, and adaptation, creating ecosystems and organisms as unique as fingerprints, yet fundamentally related through the universal principles of evolution that must operate wherever life exists, proving that while life-specific forms might be infinitely varied across the cosmos, the process that shapes life, evolution through natural selection, remains constant, an inevitable consequence of imperfect replication and limited resources operating across deep time on any world that hosts living things. How black holes warp time itself. Time is not the constant, uniform flow that our everyday experience suggests. It can stretch, compress, and slow down, depending on the gravitational environment you're in. Nowhere is this more extreme than near a black hole, where gravity becomes so intense that time itself warps in ways that challenge our intuition and transform our understanding of reality. Understanding how black holes affect time means grappling with one of the most profound insights of modern physics, that space and time are not separate, fixed stages on which events unfold, but rather a unified fabric that can be bent, twisted, and stretched by the presence of mass and energy. The foundation for understanding time dilation near black holes comes from Albert Einstein's general theory of relativity, published in 1915. Einstein proposed that what we perceive as gravity is actually the curvature of space-time caused by mass and energy. Massive objects create depressions in the fabric of space-time, much like a bowling ball placed on a stretched rubber sheet creates a depression that affects how nearby marbles roll. This curvature affects not just the paths that objects follow through space, but also the rate at which time passes. The basic principle is that time passes more slowly in stronger gravitational fields. This effect, called gravitational time dilation, has been confirmed through countless experiments. Atomic clocks placed at different altitudes on Earth tick at measurably different rates. Clocks at sea level run slightly slower than clocks on mountaintops, because they're deeper in Earth's gravitational well. The difference is tiny, only nanoseconds per day, but it's real and measurable. GPS satellites must account for this effect. Without corrections for gravitational time dilation, GPS coordinates would drift by several kilometers per day. Near a black hole, gravitational time dilation becomes extreme. Imagine two observers, one hovering far from a black hole in weak gravity, the other hovering closer to the black hole, where gravity is much stronger. If both observers synchronize their watches and then separate, the watch closer to the black hole will tick more slowly from the distant observer's perspective. This isn't an illusion or a malfunction of the watch. Time genuinely passes more slowly in the stronger gravitational field. The closer you get to a black hole, the more severe this effect becomes. At the event horizon, the boundary beyond which nothing can escape, time dilation becomes infinite from the perspective of a distant observer. This creates one of the most counterintuitive aspects of black holes. If you were to watch someone fall toward a black hole while you remained safely far away, you would see something strange. As the falling person approached the event horizon, they would appear to slow down. Their movements would become sluggish, their signals would take longer to reach you, and their image would become increasingly red-shifted as the light they emit is stretched by the intense gravity. From your distant vantage point, the falling person would never quite seem to cross the event horizon. They would appear to freeze at the boundary, becoming dimmer and redder until they faded from view entirely. This isn't because they stopped falling. From their own perspective, they would cross the event horizon and continue falling inward in a finite amount of time, experiencing nothing unusual at that precise moment. The difference is entirely due to how time flows differently in different gravitational fields. This discrepancy between what the falling observer experiences and what the distant observer sees is one of the most mind-bending aspects of general relativity. Both perspectives are equally valid. The falling observer crosses the event horizon in, say, 10 seconds by their clock, but from the distant observer's perspective, watching that crossing would take infinite time. It would never be complete. This isn't a contradiction, but rather a demonstration that time is not absolute. Different observers in different gravitational fields experience time at different rates. The mathematics describing this time dilation near black holes was first worked out by Carl Schwarzschild in 1916, just months after Einstein published General Relativity. Schwarzschild found an exact solution to Einstein's equations describing the spacetime around a non-rotating, spherically symmetric mass, what we now call a Schwarzschild black hole. His solution showed that time dilation increases as you approach the event horizon, located at what's now called the Schwarzschild radius, reaching infinite dilation exactly at the horizon. For a rotating black hole, described by the Kerr solution, found by Roy Kerr in 1963, the situation becomes even more complex. Rotation creates additional effects beyond simple time dilation. The black hole drags spacetime around with it in a process called frame dragging. Close to a rotating black hole, space itself is pulled around in the direction of rotation. You couldn't remain stationary even if you wanted to. You'd be forced to rotate with the spacetime itself. This creates regions like the ergosphere outside the event horizon, where frame dragging is so strong that everything must move in the direction of the black hole's rotation. The warping of time near black holes has practical implications for anything orbiting or falling toward them. Consider material in an accretion disk spiraling into a black hole. Material in the inner portions of the disk, closer to the black hole, experiences stronger time dilation than material farther out. From the perspective of an observer far from the black hole, processes in the inner disk appear to run in slow motion compared to processes in the outer disk. This affects how we observe black holes and interpret the light we receive from matter near them. Time dilation also affects the gravitational redshift of light, escaping from near a black hole. Light climbing out of a gravitational well loses energy, its wavelength stretching toward the red end of the spectrum. This gravitational redshift is intimately connected to time dilation. They're two aspects of the same phenomenon. A photon emitted from close to the event horizon will be dramatically redshifted by the time it reaches a distant observer. If the photon is emitted from the event horizon itself, it would be redshifted infinitely, its energy dropping to zero, another way of understanding why nothing can escape from beyond the horizon. Inside the event horizon, the warping of spacetime becomes even more extreme. In this region, the roles of space and time actually exchange in a sense. Outside the horizon, moving forward in time is inevitable. You cannot choose to move backward in time, but you can choose your direction in space. Inside the horizon, moving toward the singularity at the center becomes as inevitable as moving forward in time outside the horizon. All possible paths lead inward, and reaching the singularity becomes as unavoidable as reaching the next moment in time. The singularity at the center of a black hole represents a place where space-time curvature becomes infinite, and general relativity's equations break down. At the singularity, time itself becomes undefined in the classical sense. This suggests that general relativity is incomplete, that a theory of quantum gravity would be needed to properly describe what happens at and beyond the singularity. String theory, loop quantum gravity, and other approaches to quantum gravity propose different solutions to what occurs at this extreme limit, but none have been confirmed experimentally. Supermassive black holes at the centers of galaxies create fascinating time dilation effects on galactic scales. The black hole at the center of our Milky Way galaxy, called Sagittarius A star, contains about 4 million solar masses. Stars orbiting close to this black hole experience measurable time dilation. A star in a close orbit around Sagittarius A star, coming within a few hundred times the black hole's event horizon radius, would experience time flowing noticeably slower than we experience it here on Earth, 26,000 light-years away. Precise measurements of these stars' orbits by Andrea Ghez and Reinhard Genzel, who shared the 2020 Nobel Prize in Physics for this work, have confirmed general relativity's predictions in this strong gravity regime. Time dilation near black holes has captured popular imagination, featuring prominently in science fiction. The film Interstellar depicted a planet orbiting close to a massive rotating black hole, where time dilation was so extreme that 1 hour on the planet's surface equaled 7 years of time passing elsewhere. While Hollywood took some liberties, the basic physics was sound. Physicist Kip Thorne served as scientific consultant and later published papers about the black hole physics portrayed in the film. Such extreme time dilation is theoretically possible near a rapidly rotating supermassive black hole. Binary black hole systems, where two black holes orbit each other before merging, create incredibly complex space-time geometries. Each black hole warps time in its vicinity, and the combined warping creates regions where time flows at different rates depending on your location relative to the two black holes. As the black holes spiral together and merge, events that produce the gravitational waves detected by LIGO and other observatories, the warping of spacetime becomes dynamical, with gravitational waves carrying information about how spacetime is oscillating and rippling during this violent event. The connection between time dilation and energy offers another perspective on these phenomena. According to general relativity, gravitational fields contain energy. A clock deep in a gravitational well, where time runs slowly, can be thought of as having less energy than a clock far from any gravitational source. The gravitational redshift of light, the loss of energy as light climbs out of a gravitational well, reflects this energy difference between different regions of curved spacetime. Black holes also raise profound questions about the nature of time itself. Some interpretations of quantum mechanics and general relativity suggest that time might not be fundamental, but rather an emergent property of more basic physical processes. Black holes, where classical notions of time break down at the singularity, might provide clues about the true nature of time. The information paradox, the question of what happens to information that falls into a black hole, connects to deep questions about time, entropy, and the quantum nature of spacetime. Hawking radiation, predicted by Stephen Hawking in 1974, introduces another connection between black holes and time. Quantum effects near the event horizon cause black holes to emit radiation and slowly evaporate over extremely long timescales. This process involves virtual particle pairs appearing near the horizon, with one particle falling in while the other escapes. The evaporation means black holes have a finite lifetime, and it connects quantum mechanics, gravity, and thermodynamics in ways that hint at a deeper theory unifying these domains. The warping of time near black holes is not science fiction, but established physics, confirmed through observations and experiments. Every time LIGO detects gravitational waves from merging black holes, it's detecting ripples in spacetime that carry information about how dramatically spacetime, and therefore time itself, was warped during the merger. Every observation of matter orbiting near black holes, every measurement of gravitational redshift, every test of general relativity in strong gravitational fields, confirms that time is not absolute, but is woven into the fabric of spacetime, susceptible to warping and stretching by mass and energy, reaching its most extreme manifestation near black holes, where the flow of time slows to a crawl, and ultimately at the event horizon appears to stop entirely from the perspective of distant observers watching the inexorable pull of gravity on the fabric of reality itself. How asteroids can have their own moons. The first asteroid moon was discovered in 1993 when the Galileo spacecraft, on its way to Jupiter, flew past an asteroid named Ida and transmitted images showing a small companion orbiting it. The discovery surprised many scientists. Ida itself is only about 56 kilometers long, an irregular, potato-shaped chunk of rock tumbling through space. Its tiny moon, later named Dactyl, measures merely 1.4 kilometers across. How could such a small object, with such weak gravity, possibly hold onto a moon? This discovery opened an entirely new chapter in our understanding of asteroids, revealing that these ancient fragments of the early solar system are far more complex and dynamic than anyone had imagined. The key to understanding asteroid moons lies in recognizing that gravity, no matter how weak, still operates according to the same laws, whether you're considering a massive planet or a tiny asteroid. Every object with mass generates a gravitational field, and that field extends infinitely into space, weakening with distance, but never disappearing entirely. An asteroid's gravity is incredibly feeble compared to a planet's. Ida's surface gravity is only about 0.3 to 1% of Earth's, depending on where you measure it, on the irregular surface. But this tiny gravitational pull is sufficient to influence nearby objects, and under the right circumstances, it can capture and hold a moon in orbit. The mechanics of orbital motion around an asteroid differ significantly from orbits around planets. Planets are generally spherical, or nearly so, which means their gravitational fields are relatively simple. They approximate the field of a point mass located at the planet's center. Asteroids, however, are often highly irregular, shaped like elongated potatoes, peanuts, or even contact binaries where two lobes are stuck together. This irregular shape creates a complex gravitational field with multiple peaks and valleys, regions where the gravitational pull is stronger or weaker than average. An object orbiting an irregular asteroid doesn't follow a simple ellipse the way a planet orbits the Sun. The orbit wobbles and shifts due to the uneven gravity field. Additionally, most asteroids rotate, and this rotation causes the gravitational field to change over time from the perspective of an orbiting object. The combination of irregular shape and rotation creates a challenging environment for stable orbits. Yet despite these complications, asteroid moons not only exist but are surprisingly common. Current estimates suggest that about 15% of near-Earth asteroids have companions, and the fraction is even higher among certain populations. Asteroid moons form through several mechanisms, each revealing something about the dynamic processes that shape these small bodies. The first mechanism is capture. Similar to how planets can capture moons, though the process works differently at asteroid scales. When two asteroids pass close to each other, they normally just fly past, perhaps exchanging some momentum through gravitational interaction, but remaining on separate trajectories. However, if a third body is nearby during the encounter, it can absorb some of the kinetic energy through a three-body gravitational interaction, allowing one asteroid to be captured into orbit around the other. This three-body capture was more common in the early solar system when asteroids were more numerous and encounters more frequent. The asteroid belt, located between Mars and Jupiter, contains hundreds of thousands of asteroids larger than 1 kilometer and millions of smaller ones. In the denser environment of the early solar system, close encounters between 3 or more asteroids occurred regularly, providing opportunities for capture. Once captured, the orbit would gradually stabilize through tidal interactions and additional gravitational perturbations. Collisions represent another pathway to moon formation. The asteroid belt is a violent place where collisions occur regularly on geological timescales. When two asteroids collide, the impact doesn't necessarily destroy both objects. Depending on the impact velocity and angle, a collision might excavate a crater and eject material into space. Some of this ejected material falls back onto the asteroid, but some of it enters orbit around the shattered parent body. Over time, these orbiting fragments can collide with each other and coalesce into a moon. The collision scenario explains why many asteroid moons orbit very close to their parents and have compositions similar to the parent asteroid. If a moon formed from impact debris, it would naturally be made of the same material as the parent. Studies of asteroid pairs, asteroids with very similar orbits and compositions, suggest that many originated as fragments from catastrophic collisions that split a parent asteroid into two or more large pieces. In some cases, these pieces remain gravitationally bound, creating a binary asteroid system. The YORP effect provides a third mechanism for creating asteroid moons, and it's one of the most fascinating processes in asteroid dynamics. YORP stands for Yarkovsky-O'Keefe-Radzievsky-Paddock, named after the scientists who contributed to understanding this phenomenon. The YORP effect occurs when sunlight reflecting off an asteroid's irregular surface creates tiny torques that gradually change the asteroid's rotation rate. The effect is incredibly small. It might change an asteroid's rotation period by only milliseconds per year, but over millions of years, these tiny changes accumulate. As the YORP effect spins an asteroid faster and faster, centrifugal forces at the equator increase. Eventually, the asteroid might be rotating so fast that material at the equator experiences outward centrifugal forces that exceed the inward gravitational forces. At this point, material begins to lift off the surface and enter orbit, forming a ring or disk around the asteroid. This orbiting material can then aggregate into one or more moonlets. Computer simulations and observations of very rapidly rotating asteroids support this mechanism. Asteroid 1999 KW4 provides a clear example of the YORP effect in action. This binary asteroid system consists of a larger primary asteroid, about 1.3 kilometers in diameter, rotating once every 2.8 hours, extremely fast for an object this size. A smaller satellite, about 360 meters across, orbits the primary at a distance of about 2.6 kilometers. The primary asteroid has a distinct equatorial ridge, exactly what would be expected if centrifugal forces had been pushing material toward the equator. The satellite likely formed from material that was flung off this equatorial region when the primary was spinning even faster in the past. The rotation rates of asteroids play a crucial role in their ability to hold moons. There's a limiting rotation rate, typically around one rotation every 2 to 3 hours for a solid asteroid, beyond which centrifugal forces would tear the asteroid apart. This limit, called the critical spin limit, depends on the asteroid's size, shape, and material strength. Asteroids can spin faster than this limit only if they're held together by internal strength, essentially solid rocks, rather than just gravity. Many asteroids appear to be rubble piles, loose aggregations of boulders and gravel, held together primarily by their own weak gravity, with little internal strength. These rubble pile asteroids cannot spin faster than the critical limit without shedding material or breaking apart. The Roche limit becomes relevant for asteroid moons, just as it does for planetary moons. The Roche limit is the distance inside which tidal forces would tear apart a satellite that's held together only by its own gravity. For solid objects held together by material strength, they can orbit inside the Roche limit without being destroyed, though they experience severe tidal stresses. Many asteroid moons orbit near or even slightly inside the classical Roche limit for a fluid body, suggesting that they're solid objects with sufficient strength to resist tidal disruption. Binary asteroids, where two similarly sized objects orbit their common center of mass, represent a special category. In these systems, neither object is clearly the moon of the other. They're more like double asteroids, co-orbiting companions. The Pluto-Charon system is arguably a binary system, though Pluto is now classified as a dwarf planet rather than an asteroid. Among smaller asteroids, binary systems are not uncommon. The asteroid Antiope consists of two objects, each about 88 kilometers in diameter, orbiting their common center of mass at a separation of about 170 kilometers. These binary systems likely form from gentle collisions or from the splitting of a rapidly rotating parent body. When an asteroid spins fast enough, it can develop a dumbbell or peanut shape, elongated along its equatorial plane. If the spin increases further, the dumbbell can split at its narrow center, creating two separate bodies. Because they formed from the same parent, they initially have very similar velocities and remain gravitationally bound, orbiting each other. Observing asteroid moons requires careful astronomical work. Most asteroids are too small and distant to be resolved as disks even through powerful telescopes. They appear as points of light. Their moons are even fainter and closer to the primary, making direct imaging challenging. However, several techniques reveal their presence. Light curve analysis measures how an asteroid's brightness changes over time as it rotates. A simple asteroid produces a regular, repeating pattern, but if a moon is present, it creates additional dips or bumps in the light curve as it passes in front of or behind the primary asteroid, or as it reflects additional light toward Earth. Radar observations provide another powerful technique. When radio waves are bounced off an asteroid, the reflected signal contains information about the asteroid's shape, rotation, and surface features. If a moon is present, it appears as a separate echo in the radar data, delayed relative to the primary's echo by the light travel time to the more distant moon. The Arecibo Observatory in Puerto Rico and the Goldstone Solar System Radar in California have discovered dozens of asteroid moons through radar observations of near-Earth asteroids as they pass relatively close to Earth. Spacecraft missions provide the most detailed views of asteroid moons. After Galileo's discovery of Dactyl orbiting Ida, subsequent missions have encountered other asteroid systems. The Near-Shoemaker spacecraft orbited asteroid Eros, which has no moon, but provided detailed information about asteroid composition and structure that helped interpret observations of binary systems. The Dawn mission visited the large asteroids Vesta and Ceres, also moonless, but revealed the complex geology of these protoplanets. Future missions specifically targeting binary asteroids will provide unprecedented insights into these systems. The existence of asteroid moons has practical implications beyond pure science. Some near-Earth asteroids pose potential collision hazards to Earth, and understanding whether they have moons affects how we might deflect them if necessary. A binary asteroid system behaves differently than a single asteroid when subjected to external forces. The NASA DART mission, launched in 2021, deliberately crashed a spacecraft into Dimorphos, the moon of the asteroid Didymos, to test whether kinetic impacts could alter an asteroid's orbit, a potential planetary defense technique. The mission successfully changed Dimorphos's orbital period, demonstrating that asteroid moons respond to impacts in measurable ways. The orbital dynamics of asteroid moon systems are surprisingly rich because the gravitational fields are so weak. Other forces become relatively more important. Solar radiation pressure, the physical push exerted by sunlight, can perturb asteroid moon orbits significantly over time. The orbits slowly evolve, sometimes becoming more circular, sometimes more elliptical, depending on the specific configuration. Tidal forces between the asteroid and its moon, though tiny, gradually exchange angular momentum, causing the moon to migrate inward or outward over millions of years, potentially leading to eventual escape or collision. Triple asteroid systems exist as well, where one asteroid has two moons, or where three similarly sized bodies orbit their common center of mass. The asteroid Sylvia, about 260 kilometers in diameter, has two known moons, named Romulus and Remus, discovered in 2001 and 2004 respectively. Romulus orbits at about 1,360 kilometers from Sylvia, with an orbital period of 3.6 days. Remus orbits closer, at about 710 kilometers, with a period of 1.4 days. These multiple moon systems provide natural laboratories for studying gravitational dynamics in the weak field limit. The study of asteroid moons illuminates the processes that operated during planet formation. Planets grew through collisions and mergers of smaller bodies, asteroids, and planetesimals. Understanding how these small bodies interact, collide, capture each other, and form bound systems helps us understand the early stages of planet formation. Every asteroid moon is a relic of these ancient processes, a small-scale version of the interactions that built planets from swarms of orbiting debris billions of years ago. The discovery that asteroids can have moons transformed them from simple rocks floating in space into complex, evolving systems with their own orbital dynamics, formation histories, and future fates. These tiny moons orbiting tiny worlds demonstrate that the fundamental laws of gravity and motion operate at all scales, creating structure and dynamics from the largest galaxy clusters down to kilometer-sized rocks tumbling through the asteroid belt. Each small moon a reminder that even the weakest gravity can bind objects together across the emptiness of space. How aliens could breathe different atmospheres. When we imagine aliens visiting Earth in science fiction, they often step out of their spacecraft and breathe our air without difficulty, or they wear helmets and breathing apparatus because our atmosphere is toxic to them. Both scenarios recognize a fundamental truth. The atmosphere that sustains one form of life might be useless or deadly to another. On Earth, oxygen is essential for most complex life, powering the high-energy metabolisms of animals through cellular respiration. But oxygen wasn't always abundant in Earth's atmosphere, and even today, many organisms live without it, thriving in environments where oxygen is scarce or absent. Understanding how aliens could breathe different atmospheres means understanding the relationship between atmospheric gases and metabolism, the chemistry of energy extraction, and the remarkable adaptability that evolution can produce when organisms face different atmospheric conditions. Earth's atmosphere is about 78% nitrogen and 21% oxygen, with trace amounts of argon, carbon dioxide, water vapor, and other gases. This composition seems normal because it's all we've known, but it's actually quite unusual from a cosmic perspective. Oxygen is highly reactive. It combines readily with many elements, forming oxides that are stable and chemically inert. Free oxygen shouldn't persist in a planet's atmosphere for long unless something continually replenishes it. On Earth, that something is photosynthetic life. Plants, algae, and photosynthetic bacteria capture sunlight and use its energy to split water molecules, releasing oxygen as a byproduct. Without life constantly producing oxygen, Earth's atmosphere would gradually lose its oxygen as the gas reacted with rocks, metals, and organic molecules, eventually leaving an atmosphere dominated by nitrogen and carbon dioxide. For the first 2 billion years, or more of Earth's history, the atmosphere contained very little free oxygen. Early life evolved in this oxygen-poor world, using different metabolic pathways that didn't require oxygen. Even today, many organisms live in oxygen-free environments, deep in ocean sediments, in the intestines of animals, in waterlogged soils, where oxygen cannot penetrate. These anaerobic organisms use alternative molecules as the final electron acceptors in their metabolism. Some use sulfur compounds, reducing sulfate to hydrogen sulfide, the gas that smells like rotten eggs. Others use nitrates, producing nitrogen gas. Still others use carbon dioxide itself, producing methane. These metabolisms are less efficient than oxygen-based metabolism, releasing less energy per molecule of food consumed, but they work well enough to sustain life. An alien planet that never developed photosynthetic life might retain an oxygen-poor atmosphere indefinitely. Life on such a world would necessarily use anaerobic metabolism, breathing gases we would consider unusual or toxic. Hydrogen sulfide, lethal to most Earth animals, could serve as the oxidizing agent in alien metabolism. Organisms might inhale hydrogen sulfide and exhale elemental sulfur or some other sulfur compound. Their biochemistry would be built around sulfur chemistry, the way ours is built around oxygen chemistry. These aliens would find Earth's oxygen-rich atmosphere as toxic as we find hydrogen sulfide. Oxygen would react with their sulfur-based biochemistry, disrupting the carefully balanced chemical reactions that keep them alive. Methane represents another possibility. Methane is a simple molecule, one carbon atom bonded to 4 hydrogen atoms, and it exists as a gas at temperatures where water is liquid. Some Earth organisms produce methane as a waste product of their metabolism, and these methane-producing microbes, called methanogens, thrive in oxygen-free environments, like swamps, rice paddies, and the digestive systems of cattle. Methane is flammable in the presence of oxygen, but in an oxygen-free atmosphere, it's stable. A planet with abundant methane in its atmosphere might support life that uses methane in its metabolism, perhaps breaking down methane to extract energy or using methane as a raw material to build more complex organic molecules. Titan, Saturn's largest moon, has an atmosphere dense with nitrogen and methane, with no free oxygen. The surface temperature hovers around -180 degrees Celsius, cold enough that water is frozen as hard as rock, while methane exists as liquid in lakes and seas. If life exists on Titan, a big if, but not impossible, it would necessarily be adapted to breathe this nitrogen-methane atmosphere and might even metabolize in ways that involve liquid methane rather than liquid water. Such organisms would be completely incompatible with Earth's environment. Bringing them to Earth would be like throwing a fish into a furnace. The heat alone would destroy them before oxygen toxicity became an issue. Carbon dioxide-rich atmospheres present another scenario. Venus has an atmosphere that's about 96% carbon dioxide, creating a crushing surface pressure about 90 times Earth's atmospheric pressure, and a runaway greenhouse effect that raises surface temperatures to over 450 degrees Celsius. No life could exist in Venus's current conditions, but a cooler planet with a carbon dioxide atmosphere and might be habitable. Some Earth organisms already tolerate high carbon dioxide levels that would kill humans. Deep-sea hydrothermal vent communities, for instance, experience high carbon dioxide concentrations dissolved in water. Organisms adapted to such environments have specialized biochemistry that allows them to function despite the high carbon dioxide. Aliens from a carbon dioxide-rich world might metabolize in ways that involve carbon dioxide directly. Perhaps they would use carbon dioxide as an oxidizing agent, combining it with hydrogen-rich compounds to extract energy, producing methane or other hydrocarbons as waste products. Or they might use carbon dioxide as a raw material, building organic molecules from carbon dioxide the way plants do, but doing so as part of their metabolic processes rather than as a separate photosynthetic function. These aliens might find oxygen toxic and carbon dioxide essential, the opposite of most Earth animals. Ammonia is another gas that could potentially play a role in alien respiration. Ammonia is toxic to most Earth life, disrupting pH balance and interfering with normal biochemistry. But at lower temperatures, ammonia can exist as a liquid, and some scientists have speculated that ammonia could serve as a solvent for biochemistry on very cold worlds, potentially replacing water. An atmosphere with significant ammonia might support organisms that breathe ammonia, using it in their metabolism in ways we can barely imagine. The chemistry would be entirely different from oxygen-based metabolism, operating through different pathways and producing different waste products. Chlorine and fluorine, both highly reactive halogens, represent more exotic possibilities. These gases are extremely reactive and toxic to Earth life, but that's precisely because they're good at accepting electrons, the same property that makes oxygen useful for metabolism. An organism that evolved in an atmosphere containing chlorine or fluorine might use these gases the way we use oxygen, combining them with food molecules to extract energy. The waste products would be chlorides or fluorides rather than the water and carbon dioxide that Earth animals produce. Such organisms would find Earth's atmosphere lacking. Our oxygen, while reactive, wouldn't fit into their chlorine-based or fluorine-based biochemistry. They would suffocate in our air despite it containing a highly reactive gas. The partial pressure of gases matters as much as their chemical identity. Partial pressure is the pressure contributed by a specific gas in a mixture. For instance, Earth's atmosphere has a total pressure at sea level of about 1 atmosphere, and oxygen makes up 21% of that. So oxygen's partial pressure is about 0.21 atmospheres. Humans need oxygen at roughly this partial pressure to survive. Too little at high altitudes where atmospheric pressure drops and we suffer hypoxia, unable to get enough oxygen into our blood. Too much in pure oxygen at high pressure, and oxygen becomes toxic, causing seizures and lung damage. Aliens would have similar constraints based on their biochemistry. An alien that breathes hydrogen sulfide might need it at a specific partial pressure. Too little, and their metabolism cannot function efficiently. Too much, and it becomes toxic even to them. This means that even if two species breathe the same gas, they might not be able to share the same atmosphere if they require different partial pressures. An alien adapted to breathe oxygen at very low partial pressures, perhaps from a high-altitude environment or a planet with thin atmosphere, might suffocate in Earth's oxygen-rich air, not from lack of oxygen, but from oxygen toxicity. Temperature affects which molecules can exist as gases. On Earth, at our range of temperatures, nitrogen, oxygen, carbon dioxide, and water vapor exist as gases, while water also exists as liquid. On a much hotter planet, perhaps one close to its star, gases we don't encounter might be common. Sulfur compounds that are liquids or solids on Earth might be gases on a hot world. Metals like mercury or even iron could exist as vapor in the atmosphere of an extremely hot planet. Life on such a world, if it could exist at all, might breathe exotic gases that would condense into liquids or solids in Earth's relatively cool atmosphere. Conversely, on extremely cold worlds, gases that are common on Earth might be frozen solid. On Pluto, where temperatures drop to around -230 degrees Celsius, nitrogen, which makes up most of Earth's atmosphere, freezes into solid nitrogen ice. Pluto's thin atmosphere consists of nitrogen, methane, and carbon monoxide that sublimates from surface ices when Pluto is closest to the Sun in its elliptical orbit, then freeze back out when Pluto moves farther away. Life on such a cold world would need to breathe gases that remain gaseous at these extreme temperatures, or it would need to exist in warmer subsurface environments where different conditions prevail. The evolution of breathing mechanisms would differ based on atmospheric composition and pressure. On Earth, animals evolved lungs, gills, tracheal systems, and other specialized structures to extract oxygen from air or water. Fish gills expose blood to water flowing past thin membranes, allowing oxygen to diffuse from water into blood. Insect tracheal systems deliver air directly to cells through branching tubes. Mammalian lungs use millions of tiny air sacs to maximize surface area for gas exchange. Each system is optimized for extracting oxygen from Earth's atmosphere or water. Aliens breathing different atmospheres would evolve different respiratory structures optimized for their specific gases. An alien breathing a very dense atmosphere perhaps with pressures many times Earth's, might have very small respiratory surfaces because gases would diffuse quickly at high pressure. An alien breathing a thin atmosphere might need enormous respiratory organs to capture enough of their necessary gas. An alien breathing a gas that dissolves poorly in their body, fluids might need respiratory pigments, molecules like hemoglobin in our blood, specifically designed to bind and transport their particular gas. Some aliens might not breathe at all in the sense of moving gases in and out of their bodies. Single-celled organisms on Earth absorb oxygen directly through their cell membranes without any respiratory system. An alien with a radically different body plan, perhaps resembling Earth's sponges or fungi more than animals, might absorb needed gases through its entire surface area, rather than through specialized breathing organs. Or an alien might rely entirely on anaerobic metabolism happening within its cells, never needing to extract gases from the environment at all, living on chemical energy stored in molecules absorbed from its surroundings. The possibility of breathing different atmospheres means that habitable zones around stars become more complex. The traditional habitable zone focuses on temperature, the range where liquid water can exist. But a habitability zone could be defined for any solvent and any metabolic gas. There's a methane habitability zone at different temperatures where methane is liquid. There's a hydrogen sulfide habitability zone where that gas exists at suitable pressures. There's an ammonia habitability zone at very cold temperatures. Each zone would support fundamentally different kinds of life adapted to its specific conditions. If humans ever encounter aliens, the atmospheric incompatibility would be one of the first obvious differences. We couldn't share environments without life support equipment. An alien from an ammonia world would need refrigeration and ammonia supplies to survive in Earth's environment. We would need oxygen supplies and temperature regulation to survive in theirs. Even communication would be affected. Sound travels differently in different atmospheric gases. In a dense carbon dioxide atmosphere, sound would be lower pitched and quieter. In a thin hydrogen atmosphere, sound would be higher pitched and travel faster. An alien's voice might be physically impossible for human ears to hear without electronic translation. How aliens could breathe different atmospheres ultimately reflects the diversity of chemistry and the flexibility of evolution. Life adapts to available conditions, and the chemistry that powers metabolism is not limited to oxygen and carbon dioxide. From hydrogen sulfide to methane, from ammonia to chlorine, from thin atmospheres to crushing pressures, from scorching heat to numbing cold, life, if it exists elsewhere, would develop respiratory systems suited to its world's specific conditions, breathing atmospheres that might kill us in seconds, while finding our oxygen-rich air as toxic and alien as we would find theirs, proving that the breath of life can take as many forms as there are worlds scattered across the universe. How galaxies live and die. Galaxies are not eternal, unchanging structures frozen in the void. They are dynamic systems that evolve over billions of years, passing through distinct phases from birth to maturity to eventual decline. Each galaxy follows a life story shaped by gravity, star formation, gas flows, and violent interactions with other galaxies, ultimately transforming from active star-forming systems into quiet collections of aging stars, or sometimes meeting more dramatic fates in collisions that tear them apart and rebuild them into something new. The birth of a galaxy begins in the early universe, just a few 100 million years after the Big Bang. At this time, the cosmos was filled with vast clouds of hydrogen and helium, distributed nearly uniformly, but with tiny variations in density imprinted during the first moments after the Big Bang. Dark matter, invisible but gravitationally powerful, began to collapse first into clumps and filaments, creating gravitational wells that attracted normal matter. Gas flowed along these dark matter filaments, accumulating in regions where the gravitational pull was strongest. These early accumulations of gas were turbulent, chaotic places. The gas was cold, collapsing under its own gravity into smaller and smaller clumps. Within these collapsing clouds, the first stars ignited, massive and brilliant, burning through their nuclear fuel in just a few million years before exploding as supernova. These explosions enriched the surrounding gas with heavier elements, carbon, oxygen, iron, and others, that hadn't existed in the primordial universe. More stars formed from this enriched gas, creating a positive feedback cycle where star formation bred more star formation. A young galaxy is a vigorous place, forming stars at prodigious rates. Gas continues to fall into the galaxy from the surrounding cosmic web, providing fresh fuel for star formation. These early galaxies are often irregular in shape, lacking the elegant spiral arms or smooth elliptical forms of mature galaxies. They're clumpy and asymmetric, filled with giant regions of intense star formation where thousands of stars are being born simultaneously. The massive stars in these regions produce copious ultraviolet radiation that ionizes the surrounding gas, creating glowing nebulae visible across vast distances. As a galaxy matures, it begins to develop structure. If it has significant angular momentum, inherited from the rotation of the gas cloud from which it formed, it settles into a rotating disk. Within this disk, density waves organize stars and gas into spiral arms, elegant patterns that rotate around the galactic center. Stars form preferentially in these spiral arms, where gas is compressed by the passing density wave. The galaxy takes on the classic spiral form we see in galaxies like our own Milky Way or the nearby Andromeda galaxy. The disk of a spiral galaxy contains young hot blue stars mixed with older, cooler yellow and red stars. Gas lanes trace the spiral arms, visible as dark patches where dust blocks light from stars behind. At the center lies the bulge, a roughly spherical concentration of older stars, and at the very heart of the bulge lurks a supermassive black hole, containing millions to billions of times the mass of the Sun. This black hole profoundly influences the galaxy's evolution, though in ways that are still not completely understood. Star formation in a mature galaxy is a self-regulating process. Gas collapses to form stars, but the stars themselves affect the gas around them. Massive stars produce powerful winds that push gas away. Supernova explosions inject tremendous energy into the interstellar medium, heating gas and driving it outward in expanding bubbles and shells. This feedback can temporarily suppress star formation in regions around young star clusters, giving the galaxy a breathing, pulsating quality where star formation surges and ebbs over millions of years. The supermassive black hole at a galaxy's center can dramatically affect its evolution. When gas falls toward the black hole, it forms an accretion disk, heating to millions of degrees and emitting intense radiation across the electromagnetic spectrum. This active galactic nucleus can outshine all the stars in the galaxy combined. The energy released can drive powerful winds and jets that blow gas out of the galaxy entirely, removing the raw material needed for star formation. Many galaxies go through active phases when their central black holes are feeding vigorously, then quiet phases when little material is falling inward and the black hole lies dormant. Galaxies don't evolve in isolation. They're part of a cosmic web, connected by filaments of dark matter and gas to other galaxies nearby. Smaller galaxies fall into larger ones, adding their stars and gas to the growing giant. The Milky Way has consumed dozens of smaller satellite galaxies over its history, and it will consume more in the future. Each merger adds complexity to the galaxy's structure, sometimes triggering bursts of star formation as gas clouds collide and compress, sometimes disrupting the orderly rotation of the disk and scattering stars into less organized orbits. Major mergers, when two galaxies of comparable size collide, are transformative events. The collision unfolds over hundreds of millions of years as the galaxy's gravitational fields interact. Stars almost never collide directly. The distances between stars are so vast that even in a galactic collision, stellar collisions are extraordinarily rare. But the gravitational interactions between the passing galaxies create tidal forces that stretch and distort each galaxy's structure. Long tidal tails of stars and gas stream away from the collision site, some eventually falling back into the merged system, others dispersed into intergalactic space. The gas in colliding galaxies does collide, directly and violently. Giant molecular clouds slam together at speeds of hundreds of kilometers per second, creating shockwaves that compress the gas and trigger intense bursts of star formation. These starburst galaxies can form stars at rates hundreds of times higher than normal galaxies, converting much of their gas into stars within just tens of millions of years. The newly formed massive stars live brief lives and explode as supernovae, creating a cascade of feedback that heats the remaining gas and can drive much of it out of the galaxy entirely. The end result of a major merger is typically an elliptical galaxy. The orderly rotation of the spiral disks is destroyed by the chaotic gravitational interactions of the merger. Stars end up on random orbits, creating a roughly spherical or elliptical distribution rather than a flat disk. Elliptical galaxies contain mostly old stars, appearing yellowish or reddish because they lack the young blue stars that make spiral galaxies appear white or blue. They have little gas left for star formation, having either converted most of their gas into stars during the merger or expelled it through feedback from star formation and active galactic nuclei. Elliptical galaxies represent a kind of middle age or retirement for galaxies. They're massive, sometimes containing trillions of stars, but they're largely quiescent, forming few new stars. The stars within them are aging, slowly converting hydrogen to helium in their cores, gradually dimming as they exhaust their fuel. Over hundreds of billions of years, these stars will die one by one. Low-mass stars will swell into red giants, then shed their outer layers as planetary nebulae, leaving behind white dwarf remnants. Higher-mass stars will explode as supernova, leaving neutron stars, or black holes. As stars die, they return some of their material to the interstellar medium, but much of their mass remains locked in stellar remnants. The galaxy's gas supply dwindles, and with no new gas falling in from outside, star formation gradually ceases. The galaxy grows dimmer as its most luminous stars die and are not replaced. Eventually, in the far future, such a galaxy would consist primarily of white dwarfs, neutron stars, and black holes, the dead remnants of stars that once shone brightly. Some galaxies meet more dramatic ends. In dense galaxy clusters, high-speed collisions and gravitational interactions can tear galaxies apart. Ram pressure stripping occurs when a galaxy moves through the hot intracluster gas that fills the space between galaxies in a cluster. This hot gas, though tenuous, exerts pressure on the cold gas in the moving galaxy, stripping it away like wind pulling leaves from a tree. The galaxy is left with no gas for star formation, rapidly aging as its existing stars evolve and die without being replaced. Galaxies can also be tidally disrupted by close passes to much more massive galaxies. The tidal forces, the difference in gravitational pull between the near and far sides of the smaller galaxy, can be strong enough to overcome the galaxy's self-gravity, pulling it apart into streams of stars that wrap around the larger galaxy. The Milky Way is currently in the process of tidally disrupting the Sagittarius dwarf elliptical galaxy, a small galaxy that passed too close and is now being stretched into a stream of stars encircling our galaxy. In the very long term, over timescales of trillions of years, galaxies face a dark future. The expansion of the universe, driven by dark energy, is accelerating. Galaxy clusters will remain gravitationally bound, but individual clusters will become increasingly isolated from each other as the space between them grows. Within each cluster, galaxies will gradually merge, forming ever larger elliptical galaxies. Eventually, each cluster will merge into a single giant elliptical galaxy containing all the matter that was once in dozens or hundreds of separate galaxies. Even these ultimate galaxies will fade. Star formation will cease entirely as all available gas is either converted into stars or expelled from galaxies. The remaining stars will age and die. White dwarfs will cool, becoming black dwarfs, cold, dark stellar remnants that no longer emit visible light. Neutron stars will radiate away their heat over inconceivable timescales. Black holes will slowly evaporate through Hawking radiation, though this process takes vastly longer than the current age of the universe. 10 to the power of 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 10 to 100th power years for a solar mass black hole, far longer for the supermassive black holes at galaxy centers. The life cycle of galaxies is intimately connected to the larger evolution of the universe itself. In the early universe, galaxies formed rapidly and evolved quickly, building up their stellar populations and establishing their structures. In the current era, galaxies continue to form stars but more sedately, and many have settled into mature configurations. In the far future, galaxy formation will cease as the expanding universe spreads matter too thinly for new gravitational collapses to occur. The galaxies that exist will gradually fade as their stars die and are not replaced. But this distant future is trillions of years away. For now, and for the foreseeable future, galaxies remain vibrant systems. Star formation continues, though at lower rates than in the past. Galaxies merge and interact, transforming themselves in violent collisions that reshape their structures. New observations reveal galaxies at ever greater distances, showing us how they looked when the universe was young, allowing us to piece together the story of how galaxies live and die, how they transform over cosmic time, and how the universe itself evolves through the changes that galaxies undergo as they pass through their long but finite lifespans. Why stars explode when they die? For millions or billions of years, a star exists in a state of perfect balance. Gravity pulls inward, trying to compress the star, while the heat and pressure from nuclear fusion in the core push outward, resisting that compression. This equilibrium, this careful balance between opposing forces, allows stars to shine steadily for incomprehensible stretches of time. But eventually, inevitably, the fuel runs out. For some stars, death comes quietly, a gentle fading as they shed their outer layers and cool into obscurity. But for the most massive stars, death is anything but peaceful. When these giants exhaust their nuclear fuel, they don't fade. They explode with such violence that a single dying star can briefly outshine an entire galaxy of hundreds of billions of stars. The path to a supernova explosion begins with the structure of massive stars and how they generate energy. Stars like our Sun fuse hydrogen into helium in their cores, a process that releases energy and provides the outward pressure needed to support the star against its own gravity. But massive stars, those with at least 8 times the Sun's mass, don't stop at hydrogen fusion. When the hydrogen in the core is exhausted, the core contracts and heats up until it reaches temperatures high enough to fuse helium into carbon and oxygen. This is just the beginning. For massive stars, nuclear fusion proceeds through multiple stages, each burning a different fuel. After helium burning comes carbon burning, then neon burning, then oxygen burning, and finally silicon burning. Each stage produces heavier elements as it's ash, and those ashes become the fuel for the next stage. Each stage also burns faster than the previous one because it occurs at higher temperatures and releases less energy per fusion reaction. A massive star might spend millions of years fusing hydrogen, hundreds of thousands of years fusing helium, but only days fusing silicon. The star develops a layered structure, like an onion, with each shell fusing a different element. The outermost layers still contain mostly hydrogen. Deeper in, a shell fuses helium. Deeper still, shells fuse carbon, neon, oxygen, and silicon in succession. At the very center lies an iron core, about 1.5 times the mass of the Sun, but compressed into a sphere roughly the size of Earth. This iron core is the end of the line. Iron occupies a special place in nuclear physics. Elements lighter than iron release energy when fused together. This is what powers stars. Elements heavier than iron release energy when split apart through fission, but iron sits at the peak of the binding energy curve. Fusing iron nuclei together doesn't release energy, it requires energy. The iron core cannot generate heat through fusion. It's an inert ball of matter, supported only by electron degeneracy pressure, the quantum mechanical resistance of electrons being compressed too closely together. The iron core grows as the silicon-burning shell above it continues converting silicon into iron. Each second, tons of iron are added to the core. The core is already incredibly dense, about 10 billion kilograms per cubic meter, and as it grows more massive, it also grows hotter and denser. The electrons supporting the core are squeezed into higher and higher energy states, reaching energies where they can do something remarkable, they can merge with protons. This process, called electron capture or inverse beta decay, occurs when an electron is forced into a proton, creating a neutron and releasing a neutrino. The neutrino immediately escapes from the star at the speed of light, carrying energy away. This removes electrons from the core, reducing the electron degeneracy pressure that's supporting it. The core contracts further, squeezing more electrons into protons, creating more neutrons, removing more pressure support, causing further contraction. This runaway process accelerates catastrophically. Subrahmanyan Chandrasekhar calculated in the 1930s that electron degeneracy pressure can support a maximum mass of about 1.4 solar masses, now called the Chandrasekhar limit. When the iron core exceeds this limit, electron degeneracy pressure can no longer hold it up. The core collapses. What happens next occurs in less than a second, but releases more energy than the star produced during its entire multi-million-year lifetime. The core implodes at velocities reaching 70,000 kilometers per second, nearly 1/4 the speed of light. The outer part of the core falls onto the inner part, compressing it to densities exceeding that of atomic nuclei. At these densities, around 400 trillion grams per cubic centimeter, nuclear forces become repulsive rather than attractive. The collapse halts suddenly, like a ball hitting a concrete floor. The abrupt halt of the inner core creates a shock wave that propagates outward through the infalling material. This bounce shock wave contains enough energy to blow apart the entire star, but calculations show that it stalls within milliseconds, unable to push through the still infalling outer layers. For decades, this posed a major theoretical problem. How do stars actually explode if the bounce shock stalls? The answer lies in neutrinos. During the collapse, protons and electrons combine to form neutrons, releasing vast numbers of neutrinos. The newborn neutron star at the core, incredibly hot, temperatures exceeding 100 billion degrees, produces additional neutrinos through various processes. In normal circumstances, neutrinos barely interact with matter. Trillions pass through your body every second from the sun without causing any effect. But the matter in a collapsing stellar core is so dense that even neutrinos can't escape immediately. They diffuse outward over several seconds, and during this time, a tiny fraction, less than 1% of them, interact with the infalling material. This sounds negligible, but the total neutrino energy is staggering, about 10 to the 53 ergs, roughly 100 times the energy the sun will radiate during its entire 10 billion year lifetime, released in just 10 seconds. Even if only 1% of this energy couples to the stellar material, it's more than enough to revive the stalled shockwave and drive the explosion. The outer layers of the star are blasted into space at speeds of 30,000 kilometers per second or more. This core collapse supernova, designated Type 2 if hydrogen is present in the spectrum, or Type 1b or IC if the star lost its hydrogen envelope before exploding, is the fate of all massive stars. The explosion is so energetic that it creates elements heavier than iron through rapid neutron capture. During the few seconds of the explosion, neutrons are so abundant that nuclei can capture many neutrons in quick succession, building up elements like gold, platinum, and uranium that cannot be created through normal stellar fusion. Every atom of gold in existence was created in supernova explosions or in the mergers of neutron stars. The only direct detection of supernova neutrinos occurred on February 23, 1987, when neutrino detectors on Earth registered a burst of neutrinos from supernova 1987A in the Large Magellanic Cloud, a satellite galaxy of the Milky Way. The neutrinos arrived about 3 hours before the light became visible, exactly as predicted. The neutrinos escaped during the core collapse, while the light had to wait for the shockwave to reach the star's surface. This detection confirmed the core collapse mechanism and marked the beginning of neutrino astronomy. There's another type of supernova with a completely different mechanism, the Type 1a supernova. These occur in binary star systems, where a white dwarf, the dense remnant of a sun-like star, accretes matter from a companion star. As the white dwarf gains mass, it approaches the Chandrasekhar limit. When it crosses this threshold, carbon fusion ignites throughout the entire white dwarf, almost simultaneously, not gradually, from the center outward. The fusion releases so much energy that the white dwarf is completely disrupted. There's no neutron star remnants left behind. The entire star is blown apart. Type Ia supernovae are remarkably uniform in their energy output because they always occur at approximately the same mass, the Chandrasekhar limit. This uniformity makes them valuable as standard candles for measuring cosmic distances. Observations of distant Type Ia supernova by Saul Perlmutter, Brian Schmidt, Adam Ress, and their teams in the 1990s revealed that the universe's expansion is accelerating, leading to the discovery of dark energy and earning the observers the 2011 Nobel Prize in Physics. The energy released in a supernova is distributed across different forms. About 99% goes into neutrinos, which escape into space carrying information about the core collapse. About 1% goes into kinetic energy of the ejected material, the blast wave that expands into space. Only about 0.01% goes into light, but this is still enough to make the supernova visible across billions of light years. For a few weeks, a single supernova can outshine its entire host galaxy. The remnant left behind after a core collapse supernova depends on the core's final mass. If the core is between about 1.4 and 3 solar masses, electron degeneracy pressure fails, but neutron degeneracy pressure succeeds in halting the collapse, creating a neutron star. If the core exceeds roughly 3 solar masses, even neutron degeneracy pressure cannot stop the collapse, and the core continues collapsing into a black hole. The exact threshold remains uncertain because it depends on the equation of state of nuclear matter at extreme densities, which is not precisely known. Supernova explosions enrich the interstellar medium with heavy elements. The carbon, oxygen, silicon, and iron in the ejected material mix into interstellar gas clouds, raising their metallicity, the abundance of elements heavier than hydrogen and helium. These enriched clouds eventually collapse to form new generations of stars and planets. The Sun and Earth formed from material enriched by previous supernova. Every element heavier than lithium in your body was created in a star and dispersed by a supernova or stellar wind. The shock wave from a supernova can trigger new star formation by compressing nearby molecular clouds. The expanding remnant, a shell of hot gas and energetic particles, can remain visible for thousands of years. The Crab Nebula, visible in the constellation Taurus, is the remnant of a supernova that occurred in 1054 AD and was recorded by Chinese astronomers. At its center sits a rapidly spinning neutron star, a pulsar rotating 30 times per second, powered by the rotational energy it inherited from the collapsed core. Supernova rates in galaxies depend on the star formation rate and the mass distribution of stars being formed. The Milky Way experiences roughly 2 to 3 supernovae per century on average, though we haven't witnessed a nearby visible supernova since Kepler's supernova in 1604. Most occur hidden behind dust in the galactic plane, their light obscured but their effects, shock waves, cosmic rays, heavy element enrichment, rippling through the galaxy. The most massive stars can experience even more exotic deaths. Stars exceeding roughly 130 solar masses might become pair instability supernovae, where gamma rays in the core become so energetic that they spontaneously convert into electron-positron pairs. This removes pressure support, causing catastrophic collapse and an explosion so violent that the entire star is destroyed. No remnant of any kind survives. Stars more massive still might collapse directly into black holes without exploding at all, with all their mass disappearing behind an event horizon in silence. Understanding why stars explode when they die connects nuclear physics, quantum mechanics, general relativity, and hydrodynamics. It explains the origin of elements, the formation of neutron stars and black holes, the enrichment of galaxies with heavy elements, and the triggering of new star formation. The death of massive stars through supernova explosions is not just destruction, it's creation, recycling stellar material back into space, enriched with new elements, ready to form new stars, new planets, and perhaps new life, continuing the cosmic cycle that has built the complex, element-rich universe we inhabit today, all initiated by the catastrophic collapse that occurs when fusion finally fails and gravity wins its ultimate victory over the force that gave the star life. Why some objects in space are heavier than others. When you hold a rock in one hand and a piece of styrofoam the same size in the other, the difference is immediately obvious. The rock is heavier. This difference comes from density, the amount of mass packed into a given volume. The same principle operates throughout the universe, but on cosmic scales, the variations in density become far more extreme than anything we encounter in daily life. Understanding why some objects in space are heavier than others means understanding how matter behaves under different conditions of temperature, pressure, and gravity, and how the history of an object determines what it's made of, and how tightly that material is packed together. Start with the simplest objects in space, clouds of gas in the interstellar medium. These clouds are extraordinarily diffuse, containing perhaps only a few atoms per cubic centimetre. In comparison, the air you breathe contains about 25 billion molecules per cubic centimetre. The density of interstellar gas is so low that the best vacuum we can create on Earth is still millions of times denser. These gas clouds have mass, sometimes thousands or even millions of times the mass of the Sun, but it's spread across such enormous volumes that the density is essentially zero by any terrestrial standard. Planets show a wide range of densities depending on their composition and formation history. The gas giants Jupiter and Saturn are primarily hydrogen and helium, the lightest elements. Jupiter's average density is about 1.3 grams per cubic centimetre, only slightly denser than water. Saturn is even less dense at 0.7 grams per cubic centimetre. It would float in a bathtub if you could find one large enough. This low density reflects their composition, dominated by the lightest elements in the universe, compressed by their own gravity, but not enough to create extremely high densities. The rocky planets of the inner solar system are much denser. Earth has an average density of 5.5 grams per cubic centimetre, about 4 times denser than Jupiter, despite being much smaller. This difference comes from composition. Earth is made primarily of rock and metal, silicates in the mantle and crust, iron and nickel in the core. These materials are intrinsically denser than hydrogen and helium. Silicon, oxygen, magnesium, and iron atoms are much more massive than hydrogen atoms, and when they bond together into minerals and metals, they pack together more tightly than gases can. Mercury, the innermost planet, is even denser than Earth at 5.4 grams per cubic centimetre, despite being much smaller. For a small planet, this density is surprisingly high, and it tells us that Mercury must have an unusually large iron core relative to its size. The leading theory, developed by planetary scientists studying how planets form, suggests that a massive impact early in Mercury's history stripped away much of its rocky mantle, leaving behind a planet that's mostly iron core, with only a thin shell of rock surrounding it. The iron, being much denser than rock, gives Mercury its high density. White dwarfs represent a dramatic jump in density. These are the remnants of stars like the Sun after they have exhausted their nuclear fuel, and shed their outer layers. What remains is the core, compressed by gravity but supported by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from being squeezed too closely together. A white dwarf packs roughly the mass of the Sun into a sphere about the size of Earth, creating densities around 1 million grams per cubic centimeter, or 1 metric ton per cubic centimeter. A teaspoon of white dwarf material would weigh about 5 tons on Earth. This represents matter compressed to the point where atomic nuclei are essentially touching, with electrons flowing between them in a degenerate electron gas. Subramanian Chandrasekhar calculated in the 1930s that there's a maximum mass for white dwarfs, about 1.4 times the Sun's mass, now called the Chandrasekhar limit. Above this mass, electron degeneracy pressure cannot support the star against its own gravity, and further collapse occurs. This calculation, which earned Chandrasekhar the Nobel Prize decades later, explained why some stellar remnants become something even denser than white dwarfs. Neutron stars take density to an even more extreme level. When a massive star's core collapses in a supernova, if the core's mass exceeds the Chandrasekhar limits, but is below about 3 solar masses, it compresses beyond the point where electron degeneracy can support it. The electrons are forced into the protons, combining through inverse beta decay to form neutrons. The result is a neutron star, a sphere about 12 miles across containing 1 to 2 solar masses. The density at a neutron star's center reaches about 500 million to perhaps 1 billion tons per cubic centimeter. This is comparable to the density inside an atomic nucleus, meaning a neutron star is essentially a single gigantic nucleus held together by gravity rather than the strong nuclear force. At these densities, matter behaves in ways impossible to replicate in laboratories. The neutrons exist in a superfluid state with zero viscosity. The outer crust is a crystalline lattice of neutron-rich nuclei. Deeper down, neutrons drip out of nuclei and flow freely. At the very center, densities might exceed that of atomic nuclei, and matter might transition into exotic states, quark-gluon plasma, where neutrons dissolve into their constituent quarks, or other forms of matter predicted by quantum chromodynamics, but never observed. Black holes represent the ultimate extreme of density, though their density is somewhat paradoxical. The matter that forms a black hole collapses to a singularity, a point of infinite density, where general relativity predicts that space-time curvature becomes infinite. The singularity is hidden behind the event horizon, and we can meaningfully talk about the average density within the event horizon. For stellar mass black holes formed from collapsed stars, this average density is extraordinarily high, but for supermassive black holes containing millions or billions of solar masses, the event horizon is so large that the average density within it can be quite low, sometimes less than water for the largest black holes. This doesn't mean the black hole's interior is actually that density, just that if you calculated density by dividing total mass by the volume enclosed by the event horizon, you would get that number. The density variations we observe in the universe reflect the different physical processes that create and shape cosmic objects. Gas clouds have low density because gravity hasn't compressed them significantly. Thermal pressure from their temperature balances gravity, maintaining their diffuse state. Planets have intermediate densities determined by their composition, which depends on where they formed in the protoplanetary disk and what materials were available. Rocky planets formed close to their stars where it was too hot for ices to condense, while gas giants formed farther out, where ices could exist and helped build massive cores that captured hydrogen and helium. Stellar remnants have high densities because they are supported not by thermal pressure, but by quantum mechanical degeneracy pressure. As physicist Wolfgang Pauli explained in formulating the exclusion principle in 1925, fermions, particles like electrons and neutrons, cannot occupy identical quantum states. When you try to compress them, They resist because there are no available quantum states for them to occupy. This quantum pressure can support matter to much higher densities than thermal pressure can, but only up to certain limits determined by the mass and the type of fermion providing the support. Temperature also affects density. Hot gas is less dense than cold gas at the same pressure because the particles move faster and push outward more strongly. This is why hot air rises. It's less dense than the cooler air around it. In space, hot gas in the coronas of stars or in galaxy clusters has lower density than cooler gas in molecular clouds, even when both regions have similar pressures. The Sun's core, where temperatures reach 27 million degrees Fahrenheit, has a density of about 150 grams per cubic centimetre, dense by terrestrial standards, but far less dense than a white dwarf, even though the Sun's core is much hotter. The difference is that the Sun is supported by thermal pressure from ongoing nuclear fusion, while a white dwarf is supported by electron degeneracy pressure after fusion has ceased. Composition fundamentally determines the density any object can achieve under given conditions. Hydrogen, the lightest and most abundant element, naturally produces lower density objects than heavier elements. This is why gas giants, primarily hydrogen, are less dense than rocky planets made of silicon, oxygen, and iron. But composition interacts with pressure in complex ways. Under the extreme pressures inside Jupiter, hydrogen is compressed into a metallic state, denser than solid hydrogen would be under normal conditions, though still less dense than rock or metal. The formation history of an object determines both its composition and its density. Early in the solar system's formation, different materials condensed at different temperatures as the protoplanetary disk cooled. Close to the Sun, only metals and rocks could condense. These became the rocky planets. Farther out, where temperatures were lower, water ice could condense, providing additional solid material that helped build larger cores. These larger cores could then capture hydrogen and helium gas before the solar wind swept it away, forming gas giants. Farther still, at the coldest reaches, methane and nitrogen ices could condense, contributing to objects like Pluto and other Kuiper Belt objects. The history of compression matters too. Jupiter's core is thought to be compressed rock and ice, squeezed by the weight of the hydrogen and helium above it, to pressures millions of times Earth's atmospheric pressure. Under these conditions, materials that started as ordinary rock and ice are compressed to much higher densities, possibly exceeding even the density of iron under normal conditions. The exact state of matter under such extreme pressures remains uncertain. Laboratory experiments can replicate some of these conditions, but not the combination of extreme pressure, temperature, and scale found in giant planet interiors. Rotation affects density distributions within objects. A rapidly spinning object experiences centrifugal forces that cause it to bulge at the equator and flatten at the poles. This changes the density distribution, making the equatorial regions less dense and the polar regions denser. Saturn, spinning rapidly and composed largely of fluid, shows a noticeable oblate shape. Its equatorial diameter is about 10% larger than its polar diameter. Neutron stars spinning hundreds of times per second bulge significantly at their equators, altering their density distributions and affecting how they emit radiation. Throughout the universe, from the near vacuum of intergalactic space containing less than 1 atom per cubic meter, through the varied densities of planets, stars, and stellar remnants, to the extreme densities of neutron stars and the singularities within black holes, density varies by factors of hundreds of billions of billions. These variations reflect the different conditions under which matter exists, the temperatures, pressures, compositions, and quantum mechanical states that determine how tightly matter can be packed together, creating the extraordinary range of cosmic objects we observe, each with its own characteristic density, telling the story of how it formed and what forces shape its structure.